Welcome back for our second speaker today. It's really a pleasure and honor to introduce my esteemed colleague from Databricks, Tim Hunter. Tim has been working with Spark since the very early days, before it was actually became an open source product from 0.1.2 Spark. He actually has got a master's in mathematics and computer science from Stanford, and he got his PhD from Berkeley. And he's a contributor to MLlib and also the creators of TensorFrame, which is the deep learning package that allows you to run on TensorFlow. And today we heard about how pipelines work. They're very sequential, and they go from point A to point B in a very sequential manner. And what he's going to talk about, or what he's going to assert, what he's going to propose is, how about if you actually take pipelines and consider them as refineries? In other words, you do things in parallel at massive scale. And this is really futuristic stuff. What is coming down the pipeline with Apache Spark in terms of how do you actually take all the DAGs that you actually saw today that Misha talked about, that when you actually write your own DSL, you actually create your own tree in which you actually have the operators. But what about if you actually take that and instead of creating a one DAG, you create a forest of DAGs? And how does that actually work? So give a big hand to Tim, who's going to tell us all about going from pipelines and think of them as refineries to scaling data applications.
Thanks a lot, Jules. I mean, after such a glowing introduction, I thought I should just give you a microphone. I should just do the rest of the presentation. Thank you everyone for being here, and I'm glad that I will be able to talk to you about how to scale big data applications, not only in scale, but not only in size, but also in other aspects. So just as a quick introduction, so Spark 2.2 is currently being released, and planning has started to do Spark 2.3. And so this is why I think now is really the time to start to talk about Spark 3. It's so this presentation is not officially an official roadmap for Spark 3. It's more a reflection from using Spark since Spark 0.02, I believe, something like that, and up to the now, and it's more some thoughts about what to do, what we could change, and maybe what we should change in future releases of Spark if we were starting from zero. And there will be a small demonstration about what this could enable in the future. So I'm a statistician and I like theory. And I try to convince my colleagues that theory is useful by quoting the father of electromagnetism, which says that there's nothing more practical than a good theory. And today's presentation is about the challenges that people encounter in practice when they want to build really large Spark applications. And I would like to have a discussion with you and a perspective onto what could be some good foundations when we want to build frameworks. What are some good theoretical ideas that we can have behind it? So when the foundational paper about Spark was published, I was told that a professor in Sweden read the paper and said, "This is so obvious. This is functional programming community has been inventing that since the 70s. There's nothing new in the Spark paper." And I can be a theoretician, I can be someone interested in theory, but I still like to ground things in practical aspects. So today's discussion is not going to be some consideration about functional programming, and today we're not going to answer one big question that has been animating some theory professors about Spark, that is whether Spark is an applicative functor, or is Spark a functor, or is Spark maybe a monad? So we're not going to talk about what kind of theory it is. So what is the categorical theory behind Spark? I will be using, however, some little bit of Haskell. I don't want to frighten you. It's everything that I will be talking about after that can be implemented in any language that you can use in every day. So being Python or Scala or Java or any other language. So I'll start first about what we're used to with Spark application right now. So these days we talk about data pipelines, and when we think about the data pipeline, We usually would like to have one stream that comes on the input, one output for the team that then handles the queries, for example. And just because we want to make it a bit more complicated, we're going to store some data in a separate storage system and run some queries on top of that. But really, already in practice, if you look at what people do these days, their pipeline look more like a collection of pipelines already. We have already multiple stages with multiple inputs. This, for example, this is coming from a user that's tried to separate different jobs depending on geographical region. And it's already pretty complicated. But really, as the future goes, we are going more and more to have more inputs coming in, more outputs for different tasks, and also we need to think about how to introspect all these aspects, how to run some debugging, how to run some basics checks onto your pipelines, and also we're going more and more to mix interactive workloads with batch workloads, and also even reactive workloads that just work with just income that really get triggered by the data itself. So how can we enable this future? Because this is really far from our simple vision of a pipeline. So I really think that when we talk about data pipeline, we actually trying to coerce a reality that is much more complex than that. And we should start to think more about something like a data refinery, something which has actually a lot of pipelines and pipes going in all the directions, sometimes with some fires happening in some places, and also some leaks, all sort of things. And really, how can we manage this complexity? So when you think about pipeline, usually it has one input and one output. It's very linear. Already, if you look at current big data systems, they already move beyond just this linear representation. They tend to combine multiple inputs and have usually one output. This is essentially what you can do with a SQL query. You can select something coming from by joining multiple inputs at a high level. And this is essentially what Spark allows you when you run a single query. But really, more and more in the future, we're going to have multiple of these queries that we need to combine and then split, branch off, so that we can produce different results out of these. And this is beyond essentially a tree. Then this becomes the paradigm that we need to adopt for that is the acyclic graph, so the DAG. Also, so you're going to tell me, okay, this is all old school, because I can already have, for example, a couple of notebooks that I can orchestrate using something like Airflow, or even if you want to run multiple tasks and schedule them and making sure that they run in the proper order, you can already use something like, this is already a problem that is being solved by compilers, for example, or build systems, when you use Bazel or PANS, all these big systems. And in machine learning, you can use something like FB Learner, which lets you combine a lot of steps in the proper order. But these tools are very general. They usually assume that you're going to take something somewhere and you're going to write something somewhere else. And they don't let you put some information about what kind of data comes in and what kind of data comes out. What kind of schema are you expecting at the beginning, and what kind of schema are you expected to write or to produce after that? And they miss essentially the fact that we deal here with data pipelines. So this is why these days you tend to have systems such as Spark, which are very good for expressing data transforms. And on top of that, you have usually a complex layer using Airflow and all these tools that deal with the scheduling. So really, it's two separate systems. And you have probably been in the situation in which you modified some code somewhere, and you were expecting this code to be pushed into production, and you didn't realize that the old code was running, producing some old outputs, and then you realize, okay, I have this data which I produced. I don't know since then it is actually incorrect. I don't know since then it is maybe even corrupted. So now I need to rerun everything, and I don't know what I need to change here. So really here, we're going to see how we can control the side effects of, and how we can express the flow, essentially the flow of the data going through a system. So also at a high level, essentially any large computation system becomes an exercise in managing complexity. Because you can always write a notebook with, let's say, a couple, at least, I would say up to 1,000 lines of code, up to 100 cells. Once you are doing that, it becomes usually painfully obvious that you need to write tests, you need to move to a library. And then once you move to a library, once you work on a very large organization, how do you make sure that you can test the integration of the pipeline itself? How do you make sure that you can test each of the components independently and be guaranteed that the whole pipeline is also correct? So really, it's in the context of big data, I would like to explore a bit with you a standard question in computer science, which is, once you have built some simpler elements, how can you build something more complex and still be guaranteed that it works and it's not going to break under your feet? And finally, since we all care here about production, we are not going to simply stop the whole factory for a day so that we can swap everything and hope that it's going to work when we start again. So we need to be able to continuously make this data refinery evolve and swap some parts in the process. So if we're looking at some qualities that we would like to have from a big data processing system, here is my personal list that I would put here. The first characteristic that I would like to have is that the system should be scalable, not only in the amount of data, because this is now essentially expected for big data systems, but also in diversity. You should be able to handle thousands or even tens of thousands of input sources, and you should still be able to manage this complexity. Also, you should be able to express the dependencies between the data sets, so that if you change, for example, the schema of an input, you should be able to know what's everything else that needs to be recomputed based on these changes. Also, you should be able to write small functions, for example, that transforms a data set into another data set, and be able to compose them in a way that is scalable, so that the overall function should not let you see what is actually happening inside this function. And so finally, the last two may not be necessary in theory, but in practice, they make a big difference. The first one is that ideally, your system should be deterministic, in that if you put some data in, you should know that the answer is not going to change, which is not necessarily the case right now with Spark.
You're expecting Spark 3.0 to handle all this?
I would hope that, yes. I hope that eventually Spark 3. Yeah, so for the diversity of sources, you would have for now to write some connectors, and as we'll see, I think that for that, there will be essentially a boundary at which a connector will give some data in, and at this point, the system, Spark, should be able to make some of these assumptions internally. And finally, the last one is that computation should take less time than it needs to have a coffee break, because otherwise you're going to spend, I hope you're not like me and not spending all your time doing some coffee breaks when something takes really long to run. So how is Spark doing so far on all these points? I would say that you can do that with Spark, but it is really far from easy. And especially, and you can see it actually as the APIs of Spark evolve, because it started with a very low-level API, which you can say as a low level from a data manipulation perspective, the RDD model, which is essentially a model that lets you do all sorts of imperative transforms with some lazy aspects to speed up some computations, and some lineage information to be able to recompute these if they fail. The data set or the data frame model, which was essentially built on top of RDDs, and essentially it provides the same guarantees with some additional restrictions as to what you can put inside the data frame or inside the data set. And at the end of the spectrum, you can say that SQL model, which is fully declarative, for which you essentially cannot really modify things you cannot really modify your data sources. You can simply select something at a very high level and then just get this output. Really lets you only, is the other extreme, but in that it doesn't modify things, it will just let you manipulate and transform data. But it can really handle only one input, and it only works really well for doing one query. So I don't know if you have been in a situation in which you start with a SQL query, and then eventually you realize that because you like SQL, you'd like to modify a bit this query, add another part in the filter, add another part, add the subquery, and then you end up with a monster that takes multiple megabytes and that you cannot even print on your screen. And how can we make sure that people can still build some subcomponents without having to go down to writing these monsters? So here's a small example as a demonstration. For example, let's say that you start from loading a table, and because you're going to run multiple computations on it, you're going to cache it, and you're going to do some computation. It may take a few hours, and eventually you want to write some output after doing that. So a couple of things, and typically, so this is an example in which I was told about by a very frustrated friend, because he ran this, and then he realized that he had a typo. So it already took a few hours, and then he realized that. So then he fixed the typo, and then he realized that the directory was missing. So he runs it again, and then he realizes that his cluster is starting to behaving really weird, in a very weird manner, because he was essentially filling all the disks because he was caching, but he was never in caching. So these are all sorts of issues which I believe should be handled by Spark, and that you should not even have to deal with in practice. So really, I think that if I want to go into biblical times, some issue that we need to deal with should be eager evaluation, because here we're not able to identify all these issues simply because Spark forces us to execute, for example, this maximum command at the middle. So let's try to get rid of eager evaluation. The other one should be that when you know what the sources and what the input is, what the output is, you should be able to check whether this exists, whether you can be able to write this, whether you are able to write, or whether you're able to read. And in particular here, you should be able to check that this directory should exist. Finally, most of the resources should be managed for you. And if you make some mistakes into types or into your SQL query, the system should be able to tell you, I'm refusing to run that because I can tell you there is a mistake here even before it touches your data. So let's see what, here is some ideas about how we can see this, how we could solve that. So you can think of a data set so as a big collection of data, as essentially being a collection of elements, like we have right now with the current Spark data sets. And one principle that you can have about that is that you never actually observe you never actually access the content of the data set. You don't know how it is represented. It could be a single file, it could be a full table like Cassandra, it could be a Spark data frame, you don't know what it is. But however, you can run some queries against it. And queries return to you essentially a single element, so something that you can observe about it. And you can think of them right now as a single row, as a data set with a single row. So, for example, if you take a big data set, so let's take all the employees of the federal government, that's definitely getting into big data. And let's say that we have their names and faces and the size of their hands. And so one thing we can observe about this is how many elements we have and the size of the largest hand. So that's one operation we can do about that. The other operation we can do is transform this data set. So let's say, for example, that we evolve in time. They start to take some different roles in the government. And, and then we can do some other observations on this data set. So one of the problems is how we can deal with, so one idea that we can have is that what you can observe about the data set, so what you can observe about that doesn't depend on how this data is being structured or laid out in different systems, which Spark doesn't respect right now, because in Spark you can have access to partition IDs, you can, or in the most subtle way, you can use the RDDs to build counters and indexes of the elements. And these indexes will depend on how the data, how many partitions you have. So let's say that we cannot do that. Let's say that we ban this operation from the API. And it turns out that if you look at if you look at the consequences of doing that, you have some very nice mathematical properties about the kind of operation you can express. So it restricts you, it puts a bit more restriction as to what you can do, but you can have some strong backgrounds. You're on safe grounds from a theoretical perspective. So a last assumption that we can do is about reading and writing. So you can say that when you want to write something, you only observe what you are writing, and if another system, such as Cassandra, decides to also override this table, this is not something that the system will see. The system will just assume that it will see all the changes it is making itself. And we'll see in the demo, actually, what kind of, so it can, combined with determinism, it enables us to remove a lot of computation and do a lot of optimizations under the hood. So just to make it a bit more concrete, for example, if you have a data set of integers, and you can make some observations about it. For example, you can compute the maximum, and instead of, Spark would directly give you the maximum. In this system, you essentially, if you are used to Scala, you would get essentially a future, or essentially a box that will contain eventually the value, and that you can use later. It's, I think an example will make it more concrete. You can also take two data sets of the same type and combine them by making the union. You can collect the elements locally, and so on. So I have yes.
Sorry, you trying to abstract away like partition sizes and locations? I think that sounds like a great concept. I worry about that all the time. But how does that work?
So this is yeah. So your question is, okay, this is nice on paper, or actually on electronic paper here. You would love it. Okay. You are jumping 2 slides away, just like that. I'm going to show you what it could look like. And so, speaking about implementation, I wrote a quick prototype of this principle on top of Spark using Haskell, and it works by letting you write some your queries, and then it outputs a sequence of logical plans that it feeds to Spark, or it could feed to other systems. And eventually, and then return to you the results only when you request these results. So the general principle that I had when I was writing it is that it will refuse to run anything until it is really sure that what you are going to run is correct, that you don't have typos, that your types are correct, that you can write what you can, and so on. And there is a number of correctness checks that are being performed. So. And eventually, it could become a global optimizer for your complete pipelines. We'll see some examples as to how this is possible. So let me switch to a demo. Okay, so I have this this notebook here, written in so it's written in Haskell, but essentially, as you will see, the language doesn't really matter. So let's say that I have this small data set here, and this is saying that I have a data set of 4 elements, I'm going to make, and I'm going to load it. So here, this data set is of type integer. We also know that it is of type integer from, the system also knows that it is of type integer, and it corresponds to saying that we're going to distribute some values. So now what we can do is count it. And in Spark, if you were to run count on a data set, it would trigger some computations. But here, all it is going to do is that C, so the count, is a box value, and it is of type integer, but it hasn't run anything so far. And we can still continue to do some operations with this count. So for example, we can add some values, and then it tells me, okay, now I have, the result is the addition of some number and some other number. But so far, no computation have been run. I'm simply expressing chaining of operations in a very lazy manner. And of course, now you are wondering, okay, how does it look like? What is it? So I'm reusing some interface from TensorFlow, which lets you show what the graph of computation will look like in the background. So, for example, so this is our output here, x, and I can see that it's a local value, so it's the result of collapsing your data set. So the Spark will see that it is of type integer, and you can see that it depends on a constant here, and here it depends of a list of value. So this is of course a toy example, but we can see later how it can help in really complex operations. And of course, it's nice to express these computations, but now let's run them with Spark. So in the background I have a local version of Spark running, and let me connect to Spark using. So here I have a context running in Haskell, and I'm going to call this function, which is part of this library, which takes a local data and then asks Spark to run the computations that correspond to it. So let's see, yes, okay, so it ran, okay, finished, and in the background, this graph that you saw here, this graph of computation, got translated into essentially a JSON representation, got sent to Spark, and Spark ran some computations, and returned the result. And this is running using a standard REST API, and you can actually query the background, query the backend. So here, the name of this operation was this ugly name, and you can ask Spark to give you the you can ask to the REST API to see the result here. So this is independent. The Haskell part is just to model the elements, but Spark is doing the rest in the background. So, okay, so some people told me this is useless. Because this is essentially just doing some lazy computation on Spark, and Spark is not fully lazy at this level, but it can already do a lot of things. And this would give you could write all of that in a notebook, and it would look maybe a bit less complicated. Well, most of these, so one thing that you can infer from looking at this graph is that a lot of operation in Spark, such as select and filter and combine, and for example, and dividing by constant and so on, correspond actually to a very small set of primitive actions of combining data sets with local values with local values. And you can have some very good composition rules to express a lot of optimization after that you can do to completely rearrange the computations if you want to. So behind the scenes, I won't show some of the optimization, but behind the scene, you can actually rewrite the complete program as long as you can still give the observables, the local data back to the user. And also you can, and I'm definitely not a SQL expert, and you can combine that also with a lot of optimization that have been already found in the SQL database community. So let's see how we can deal with input and output. So when you write files, this is an operation that you can observe. And since the operations are deterministic, and since the results are being cached, you can actually remove, if you read again from some sources you know about, you can actually remove a whole bunch of operations that you know have already happened. So let me show you what it would look like in practice. So, okay, so I need in Haskell to have all these imports. Someone told me that Haskell is called the language of the 100 imports, for good reason. Okay, so I am connecting. So I have this small file here that, let's say, contains some names and salary information. I don't know what kind of money is that, but it's definitely not dollars. Bitcoins? Yeah, you wish. And okay, so here I'm asking, so I'm using this function here to say that infer the schema for the on this JSON file, and give me back a data frame that contains the information. So okay, so it tells me at the end it found, so it could load it, and it's going to be a source of data with so some optional string value and some optional integer value. This is done by Spark under the hood. So let's say that we want to collect this information to see what it contains. We're going to collect this enormous collection of four points here. It's so this is the operation that would happen under the hood. First, Spark would use a data source to read the data as a data frame, and then it would call a collect operation to build to retrieve the content. So this is code that just to show what would happen under the hood. So under the hood, this system is going to look at the file. So it found that we're going to look at this file, and it is going to retrieve the timestamp corresponding to the file. And it is going to insert this information into the graph of computations. So based on, since all the operations are deterministic, you can assign some IDs, for example, to each of the nodes of this graph that are just based on the content and on the operation that depend on it. So I'm going to run it, and this is going to be what we expect. So we get the list here of elements, and let's say that we want to run it again. So if we were to run it again, then the system knows that it has seen this timestamp before. It knows that the operation are all deterministic, and so it doesn't need to run anything, actually. It can just say, I'm going to give you a placeholder that refers to existing result that already got computed before. Because unlike Spark, when it sees, for example, a map operation, your regular Spark cannot make this assumption because, for example, as in the presentation before, the map function was used to also do some side effects, to do some other operations. Here, since we know that the side effects are going to happen later when we write, and they are the only ones being allowed, we can simply remove this whole reading and inferring schema and everything by just saying, here is the result. Because we know that the file hasn't changed since the last time we checked it. And for example, if I give a big raise to this person here, and if I try to rerun it, it is going to see that the file changed. It's going to reinsert a new operation for doing the reading. And actually, you could see that by saying that the ID here has changed. It incorporated into the ID the fact that the timestamp. And then when you run it, you would have the new information. So these are the kind of optimization that you can do. And of course, this is a very small graph here. I'm just reading and then collecting. But you can see how you can, if you have very complex graphs, if you decide to rerun, essentially this is a no cost operation in this kind of system. So just to see what, just to make sure that we are on the same page. So here you start by saying that I want to read this file and I want to do some counts. Based on the timestamp and based on, you can say, okay, this is the some hash that I'm going to associate to this node in the graph of computations, and count depend on this one. can't depend on this node. So it's going to, you can compute those, you can also calculate the hash just depending on that. And let's say that you want to run again the computation and then do some other extra operations. So you would be able to calculate the hashes again, check first on the full files to see that the timestamp hasn't changed, recompute the hashes and click the last element, and then you would see, oh, I've already seen these hashes before. Let me just remove that and have a pointer to some previously computed value. No need to recompute that. So this is just what the system did. Okay, and finally, another big problem that comes, so usually a big problem that comes when you want to see some complex graphs is when you have, especially when you look at the Spark UI, and I see it in particular in machine learning jobs, where you have usually pretty complex operation on the data frames. When you look at all the operations, it's really hard to know what this map RDD corresponds to, and especially when you have 20 stages one after the other. At this point, you need to become the expert of the algorithm to understand which operations are happening. So is there a way that we can relate more easily the code to all the operations being done and presented to the user? So let's take a look at that. So I'm going to load this. So I'm going to have a small data set again. And I'm going to just find, and let's say that so let's say our data scientists have written a couple of functions for us. One of them was the mean. So given a column containing integer, containing some integer values, it returned to you the mean of the elements. So it would take the count, it would take the sum, it would convert them to doubles, and you can also assign some names to these operations. It's all lazy. So essentially you are adding names to nodes in your graph. And then you can return then you can divide, and then that's how you get the mean. So this function is all lazy. All it computes is operation that it computes some observables and then combine them, but will not compute any result. Spark here would be forced to compute some results because it's not lazy at this point. So then you can see how you can then combine all these operations together. You can compute the mean, center your column, then you can scale it by the standard deviation, and so on. So let me run that. So at the end, all the user see if the user wants to use it is this function, which depends on a few other functions, which takes a column of data and then return to you a new column, which has been transformed and rescaled. So let's see what it looks like. So if you look at the graph of computation that happens behind the scene, it starts really to get complicated. So you would start here from our data set. Then you would compute count. You would compute sum. You would combine it with mean. And you can see already that the system has decided that the count here that I computed, I can reuse it for the standard deviation. That's something that the users don't even need to do. This is an automatic optimization. So you can see how when you have really complex graph, a lot of things can happen, can be unrolled for you under the hood, thanks to determinism and laziness. And finally, there is final select here. And in between, there is a number of combining and shuffling operations. So this looks pretty complicated, but at least we can see that these names here correspond to other names that we have as references in the code, so we can relate to which operations got generated by which functions. So let's run it. Okay, yeah. And as an additional step, let's see what Spark actually did under the hood. So this is the graph of computation that Spark performed under the hood. So, for example, if we look at this operation, we can see that when it decided to make a sum, it did actually a couple of partition. It did a couple of it did one shuffle, which is the final one, then another map partition, and some other operations. And you can also trace back in your code, like you would with Spark, where this operation, where this code happens inside the backend. And one aspect which is not available right now in the current visualization of Spark is the fact that here you can put names to blocks of operations. So you would know that these operations on RDDs correspond to computing this, for example, this element here. And you can see how this kind of, and also you keep also the dependencies between the operations. So, and for example, here Spark decided by itself, since it was local values, it decided to run 2 jobs in parallel, one for computing the sum, one for computing the count. So even though they depended from the same data set, since it was constant values, Spark could just start to run 2 jobs in parallel. And some other kind of optimization like this are available under the hood. So, of course, this is done using a fairly esoteric language. So I would like eventually to work on a Python interface, which also would let people have, for example, a pandas backend instead of using Spark. So imagine a place in which you could use pandas to check if your functions are correct. And then once you decide when you want, once you want to run it at scale, you can just say, go Spark. And you know that the results are going to be the same on the same data sets. Also, group by and SQL can have some interesting optimizations here, but that I will not cover. So as a conclusion, really, we can see how so it's very clear that now Spark has enabled already a lot of applications that were hard to be possible before. But as you scale in an enterprise, as you start to have a really complex pipeline with a lot of dependencies and with a lot of steps that you would like to organize in a way, we need some better ways to manage the complexities of all these data flows. And so one approach to deal with that is to look at what the functional world has been doing for decades now, and Spark will really provide a solid foundation for these abstractions. So I think that by adding a little bit more laziness to Spark, and that by making the APIs even more declarative than what they are, then we can go really far in that respect. So you can try this out if you are adventurous. All this code is open source. And there is no change related to, the only change that you need to do on the Scala side is to run a Spark package, which is already published, that you can embed inside your regular Spark. So, as Jules mentioned, the Spark Summit is coming fast, and I think Jules gave me also a discount code if you want to go there. And I think we'll be presenting some of these aspects over there. So thank you, and I'll be happy to take a few questions.
Give a big hand to Tim, guys.
Yeah.
Fun stuff.
I'll repeat your question if you say it.
Yeah, go ahead.
My question from the user perspective, something that you didn't mention is that data frames, for now, do not perform really well, I would say. I'll tell you an example. I did a program where I had to enter the missing rows, basically, in the data frame. And I tried to do this by sliding window, completely in the Spark environment. And once I collected everything and switched to simple lists, my performance improved 100 times. But yeah, everything was for the single RAM memory, basically. So every time I had to check the memory and write back to the data frame, all those things. So I mean, just to think for future, you can think about simplifying the data frames because they have really huge metadata behind them.
Yeah, definitely. And also there is, so data frames were introduced in a couple of releases ago, and since then, it's pretty clear that at least 1 or 2 releases ago, if you're writing some very naive code by hand to do some of the operation that you express with the data frame, you were getting some terrible performance coming from data frame side. There has been a lot of efforts, especially with Spark 2 and like 2.1 and 2.2 is continuing, to improve the operations of first of the most popular operations, and eventually we'd like to get to the more comprehensive ways of doing that. And then I think this kind of horrible performance will actually go away as more and more of these optimization is getting pushed into Catalyst, the engine behind Spark.
Do you mind putting your use case and your problem on the user list, so some of our guys who are actually working on the SQL engine can actually have a look at it, because it seems to be, if this is a problem that we actually see everywhere, we would like to address it. Any other question? Brilliant.
So let's take the Grammarly example where you had to unroll the writes to 3 different targets. How are you going to help that?
Sorry, to do what?
If you take a look at the work that was described in the Grammarly, the second talk, about how they were writing to Cassandra and then a Kafka pipeline, or maybe 2 Cassandras.
Yeah. So
how are you going to prevent us from having to unroll things like they had to do?
So if the problem is to the problem is at the writing step, then you can. So this was a small example using just HDFS tags, but you could definitely have more complex analysis of what the data sync is capable of supporting and what kind of information it can provide. And then you should be able to get actually a unique timestamp or hash to say this is what the data is, or this is what the data is already there.
They have a different problem. They need to write to 3 different locations.
Oh yes. Oh, the pipelining. Yes. Yeah. So well, for that you can cache. So I didn't show how you can cache the data, which is also another thing. But in terms of writing to different sinks, each of the sinks should be able to be handled independently and be able to write them. Because even though here in that particular case, even if the all the writings, if I understand correctly, were done sequentially, first to Kafka, then to Cassandra, then to another store, right? And in that case, you could write the same code as an operator that you plug into the graph, and it should be able, and then you can parallelize these operations.
I think if you look through his example, his step 3, that requires knowledge of partitions that you're trying to remove. And he showed that caching didn't work, and he showed that
Yes. So, at a high level, the user doesn't necessarily need to know. Well, so if you express the operation at a high level, I would hope that you would just have to write to the source, or sorry, write to the sink. However, as a developer, of course, when you write the operation that corresponds to that, then you need to know about the partitioning, and then you can do some, and then you are aware of what the source can do. Another thing I didn't show about the writing is that the data sync API for data frames and data sets supports partitioning and a lot of layout operations, and these could be available as well in this kind of framework.
So we're going to hang around. We have to end. We are past over time. We want to thank Adobe for hosting us and giving us this beautiful environment. Grammarly, guys, give them a big hand. Tiffany, she's hiding back there. She did an incredible job. Don't forget, our next meetup is going to be in Palo Alto at Salesforce. The meetup page is up. Do register it, and hope to see you at Spark Summit as well. And thank you all for coming. We appreciate this momentum of Spark users we actually building day in, day out. So thanks a lot for coming, and drive home safely or take the BART or whatever it is. Cheers, guys.